So, welcome back to lectures on engineering mathematics 2, and this is lecture number 24 on determination of roots of algebraic and transcendental equations. So, today we will be talking about the several methods numerical methods that can be used for determining the roots of algebraic and transcendental equations. One of them is the bisection method, one of the simplest approach to get roots of algebraic and transcendental equations. The second approach, we will be talking about the fixed point iteration method, and then there are two more approaches which we will cover in the next lecture. So, Newton-Raphson method and secant method. So, basically these four approximations algorithm will be talking about in two lectures. So, the first two will be covering in this present lecture, and the next two will be the topic of next lecture. So, coming to the bisection method, it is based on the following theorem of for zeros of continuous functions. What is this theorem? That given a continuous function f from this a b to r, such that f a f b is less than 0. So, the product of the value of the function at a and f at b is negative, and that indicates that. So, for instance, this is a and this is b. So, one for example is positive and another way it is negative, or it can be negative at a and then it can be positive at b. So, that the product is always negative. So, one of them is positive and the other one is negative, then only this is possible. So, naturally if the function is continuous, it will cross the x axis. So, it must have a root then. So, that is the principle behind this bisection method, which we will be exploring a bit more in this lecture. So, there exists alpha in this interval a b, somewhere in between a and b. So, that f alpha is 0. So, this is exactly the point alpha where this graph of f meets x axis. So, based on this principle, we will develop an algorithm to find zeros of a continuous function, and the outline of the algorithm is as follows, that we choose the interval I naught, that is the whole interval a b, which makes sure that there is a root between between the points a and b, or in the interval a b. So, we are calling this, let us say I naught, this interval a b, which has this property or which ensures that there is a root in between a and b. The bisection method generates a sequence of the subintervals, that means we are calling it I k. So, k greater than equal to 0 or greater than equal to 1. So, I naught is already defined. So, we can go with let us say I 1 also there. So, a naught a 1 b 1 and a 2 b 2. So, we will go for the sequence of subinterval, and what will be the property of these subintervals, that the subinterval here will be the subset of the earlier one. For example, I 1 will be the subset of this I 0, and I 2 will be the subset of I 1, and so on. So, basically we are narrowing down the interval, subsequent interval, and what is the property of these intervals? So, these end points, again every time this property is fulfilled, that f a k b k f b k is less than 0. That means, while narrowing down the interval, we are making sure that the root lies in this new interval. So, this process of narrowing down the interval will lead to the root at the end, or in the case when this k approaches to infinity, that we will also show that this process will lead to the determination of the root, or every time we are narrowing down the interval, that means we are getting a better approximation for the root, because this condition makes sure that the root lies between this end points of the new interval. Well, so just a pseudo code which can help immediately to code or the write a program in the computer. So, what we will do, we will set a naught b naught as the given interval a b, which has the property that f a f b is less than 0, and then we will take the middle point. This is what the bisection, the name is also coming. So, we are bisecting the given interval into two equal parts by taking this as x naught, which is the middle point of the two end points, and then the algorithm will go as follows. So, now we will check for k greater than equal to 0. So, let us say k is 0. So, we will check whether a 0 or x 0 is negative. If this is the case, that means we have, for example, this was a and b, which we are denoting as a naught and b naught also, and then middle point we are calling it as x naught, and then we are checking whether this f. So, the function value here and function value there, they have this property that the product is negative. That means the root is somewhere in between this interval, and if this is the case, we will set now the new interval as the left point of the new interval, again a, because our interval is this one now, because we know that the root lies in this interval, and the other end of this new interval will be x naught. So, this b k plus 1 will become x k. If this is not the case, then f x k into f b k will be negative. One of them will be negative because there is a root in between. So, either it will be there or it will be between x k and b k. So, if it is between x k and b k, we will set our interval accordingly. Now, the left point we will take x k and the right point we will take b k. So, our new interval is set now, and then we will go for the middle point again as x k plus 1, and then we will move for iterate for this k to get these sequence of these x k's, which are actually the approximation of the root. And from the algorithm, it is clear that as we move further, the x k will be a better approximation certainly. Coming to the geometric interpretation, which is also clear, which was clear from the algorithm, but we can again look into it. So, suppose this is the curve of this y is equal to f x, and then these are the 2 points a and b, where we are sure that there is a root. So, f a and f b is negative. So, this graph will certainly cut this x axis somewhere. This is the interval I naught in our notation, and then we go with the middle point. So, that is x naught, and what do we see, that there are two intervals now. One is this side here from a to x naught, other one is here from x naught to b. But that condition again we will check whether f a x naught, the product of the function value at a and x naught, or x naught and b, which one is negative. So, certainly because root lies here, so the other one will be negative. So, we will have this I 1, our interval of interest is I 1, which is the right hand side of this whole interval. And now, so this is again we will take the middle point. Suppose this is x 1, and then again with this criteria of checking where the root lies, and it will lie obviously in this left interval now. So, the root will lie here, and therefore, the I 2 will become this interval from here to here. Again we will go for midpoint and then see that this is I 3 and so on. So, we are narrowing down this interval, and then the middle point of it will give the approximation of the root. So, as we proceed further, we will have a very small interval, and then again midpoint of this interval will give the approximate root of this function f x. Well, so talking to the convergence of the bisection method, which is the beauty of this method is that it always converges, which we can see again mathematically, though geometrically it is clear that it will converge because we are bisecting the interval always into two parts and narrowing down the interval. So, certainly it will go to the actual value as k approaches to infinity. So, we denote the length of this interval by I k and the absolute value here. So, b k minus a k the absolute value, we are denoting the length of the interval, and we know that f alpha is 0. So, we are searching for this alpha, and note that this I k is half of the I k minus 1. So, the I 1 is, for example, the half of the I naught, the length of I naught, or I 2 is half of the length of I 1, because we are bisecting the interval every time. And by just induction we can see, because here we have like I 1 is I naught by 2, and then I 2 if we go, then that is I 1 by 2, and I 1 is already I naught by 2. So, it is a 2 square. So, I 2 here is giving us this 2 square, I 3 will give 3 square, and so on. So, I k is giving here 2 power k with this I naught, and I naught is like nothing but the b minus a, that is a beginning interval, which is b minus a. So, we have this relation that the length of this I k is equal to b minus a divided by 2 power k. And now, if we denote the error by this x k minus this actual value alpha. So, this is the approximate value, this is the actual value. So, this is the error E k, which we are denoting by x k minus alpha, and what we know also that this error will be less than I k by 2. Why so? So, for instance, consider I naught. So, E naught. So, the error at the beginning. So, what is the E naught? E naught is just the x naught and minus the alpha. So, x naught is somewhere there and minus alpha, which is somewhere in this interval. So, this x naught minus this alpha, if we look at, it must be less than the half of the interval I naught, because I naught was from there to there, and then x naught was the middle point, and we know that somewhere in this interval a to b the root lie. So, definitely the difference between this x naught and alpha will be less than half of the interval length. So, this is what we have written here. So, this will be less than the interval length by 2, because this is somewhere in between, this is somewhere, this is exactly in between, and this is going to be either the right side of this or the left hand side of this. So, this distance between x naught and alpha will be certainly less than I naught by 2, and the simple logic can give us in general that E k will be less than I k by 2. So, having this, now we know the relation of I k, which we can substitute from there, b minus a 2 power k plus 1, and this is true for all k. And then if we take the limit that k approaches to infinity, so this will go to infinity here, and then b minus a is some number. So, going to infinity means this will go to 0. So, the error will definitely go to 0, which is clear from the geometrical interpretation as well, or mathematically we can see here. So, what is the advantage of this bisection method? That it is globally convergent. The convergence is global, we do not have to worry, we do not need any other condition than to have this continuity of the function, and which has some root in a given interval. So, we have to find that interval. So, once we have that, the convergence is guaranteed, we do not need any other condition on the function or its derivative, etc. So, that is the main advantage of this method, but the disadvantage, if we talk about the convergence, is not very fast, because we are just dividing this by half and half. So, it is a kind of linear convergence, which is the only drawback of this bisection method. So, we can perform here 5 iterations of the bisection method to obtain the smallest positive root of the equation. So, first we have to realize the interval where this root lies, and that is another difficulty which always we have in all kind of iterative method, that we have to choose some initial guess. So, here the initial guess is the interval we have to find, and if we take actually the actual root, because in this case we can find out. So, there are 3 roots here, the smallest is actually 0.201 close to this 0, other 2 are 2 and then minus 2. So, if we look at this equation also, so we have f 0 as 1 and f 1 is minus 3. So, this there is a root between 0 and 1, and certainly that is going to be here the smallest root we have. So, f 0 and f 1 is less than 0. So, there is a root in this interval 0 and 1. So, we will do the initialization in our algorithm, that a naught we will take 0 and b naught we will take 1, and then we will go with the x naught, which is the middle point, as 0.5. So, 0 plus 1 by 2, it is a 0.5. So, this is our first approximation, 0th approximation or initialization, which says that x naught is 0.5. And now we have to check whether the root lies, now we have bisect the interval. So, we will see whether the root lies between 0 and 0.5 or it lies between 0.5 and 1. This is what we have to check. So, we have to check the condition. So, in this case we observe that f a naught and f x naught, this is less than 1, that means the root lies between 0 and 0.5. This is the way we will find the next interval. So, let us go with the iterations. So, we have already seen that 0 1 then 0.5, and we have observed that this root lies between a naught and x naught. So, as iteration first, after this initialization here, what we will do. So, a 1, now we will check a 1. So, a 1 is 0. So, a 1 we have taken the 0, the next interval, the left boundary is 0, and the right boundary we will take 0.5, where the function is negative, here the function is positive. One can always check, but has to check basically whether the sign of this function. Then we will go with the middle point of the 2 here, a k b k, this is the middle point x k. Here again we have to check the function value, whether it is positive and negative. So, it is coming as negative in this case. So, what we observe here, it is positive, here it is negative. So, the root lies between exactly this interval 0 and 0.25. So, we will set, then this is our interval and 0.25 will be our interval, and then we will take the middle point here 0.125 and check again the sign of the f is positive there. So, here it is positive, here it is positive. So, there is no root between this. We will have a root now in this interval, f positive, f negative. So, our interval will become now 0.125 and 0.25. So, 0.125 and 0.5 is the new interval, and then again the middle of this will give 0.1875, and here f is positive, here f is positive, but here f is negative. So, now this will give the new interval, because x k and b k, this product is less than 0. And so, our new interval, it is 0.1875 and this is 0.25, and again we will take the middle point here. So, we have the new value 0.21875 and f is negative there. Having this now, so it is positive negative, that means we know that the interval is now, after this 4th iteration, our new interval is 0.1875 and 21875. So, the root lies in this 0.1875 and this 0.21875 after 4th iteration. So, the x 5 we can get now, just the middle point of this. So, we will take the average here, and the average will give this 0.20 and 3125, that is the x 5 after the 5th iteration. So, we can see it is the actual root was also 0.20 something. So, it is matching, it is getting closer to this after even 5 iterations. If you go further, naturally this root will improve. So, this is a simple algorithm which we can, which we have demonstrated with this simple example, and it is always just checking the interval where the root lies and then narrowing down the interval, and that is all. So, it is a very simple algorithm to compute the root of a function. The another algorithm which we will be talking about, another method, that is fixed point iteration method. So, it is a proper iteration method which we will now discuss. So, the idea of general, indeed a general iteration method lies on this principle that if we rewrite the given function f x equal to 0 in this form, that x is equal to g x. So, we will rewrite our f x equal to 0 equation into this form, x is equal to g x. We will bring x one side, everything else we can take to the right hand side. So, that we have this form x is equal to g x, and once we have this form x is equal to g x, we can set up the iteration, because finding x from here, x from this f x equal to 0, that is the root, we have already written as x is equal to some other function g x. So, here also we are looking for a x which satisfy this equation, and that means that is the root of this equation. So, to search which x satisfies this equation, we set up the iteration at this point by saying that this is x k plus 1 and g x k. So, we will choose the starting value, approximate value, here let us say x 0, compute g x 0, we will call it as x 1, then x 1 will go here, then we will call x 2, x 3 and so on. This will be a sequence of the approximations, and we will show that such a sequence under some condition converges to the actual root, not always as in the bisection method. So, the convergence will naturally depend on that how we rewrite this f x equal to 0 to x is equal to g x, that is what the convergence actually depends. So, because there are various ways we can rewrite this f x equal to 0 in this form x equal to g x. I mean, this is not a unique way that we have to write this f x equal to 0 in this form. So, there are several ways, and the convergence will depend naturally, and we will demonstrate this, that how do we define this g x. Why this fixed point name has come for this method, because the point this x star is called fixed point of function g if we have x star is equal to g x. So, a function is given, for example, g x is given, and a point x star is called the fixed point of this if we have this property that x star is nothing but g x star. So, based on this, because we are looking here for this fixed point of this g x, we are calling this a fixed point iteration method. So, having this f x equal to 0, we rewrite into x is equal to g x, and there could be several forms, it is not unique. For instance, we can take g x x x minus f x. So, what we have now here, for instance, x is equal to x minus f x. If we have taken this, x x gets cancelled, and again we will get f x equal to 0. So, this is the function, one of the functions g x we can always choose as x minus f x, and this is nothing but this is equivalent to saying that f x equal to, so x is equal to g x here will give exactly f x equal to 0. So, this is one of the function which we can work with. Another one we can say x plus 2 f x. So, there are various ways to define this. Here we have like x is equal to g x. So, x plus 2 f x, again x x gets cancelled, and then we will get again f x equal to 0. So, several ways, not only 2, we can have 3, 4, 5, whatever. So, this is one way. So, there are infinitely many ways to define this g x. One more possibility which is a little bit complicated, we can have x minus f x over f prime x, for instance. So, here also x is equal to g x. If I put this g x there, f x over f prime x, and this gets cancelled, and then again we will get f x equal to 0. So, this is also equivalent to f x equal to 0. So, here indeed this particular g, which leads to another method, Newton-Raphson method, which we will discuss in the next lecture. So, what we have seen here, that there could be infinitely many possibilities for defining g x. Now, we will be talking about that which g we should choose, so that the convergence is guaranteed, and this is what we have here, the sufficient condition for convergence. So, if this g x is continuous, that is a very natural condition we have here in some interval this a to b, and that contains the root. So, we have an interval where the function is continuous, and we are sure that this interval contains the root, and then we have, if we have this g prime, the derivative of g, the absolute value of the derivative of g less than equal to rho, and it is less than 1 in this interval. So, in the interval a b, if we have this condition that the derivative is strictly less than 1, then for any choice we take, any initial choice we take in this interval a b, the sequence x k. So, we are getting x 1, x 2, x 3 and so on, and this sequence will converge to the root. This is what we will observe now. So, going to the sketch of the proof. So, we consider this error here, x k plus 1 minus this x k x star is the actual fixed point. So, the root of this equation f x equal to 0. So, x k plus 1 minus x star, x k plus 1, from the algorithm we have g x k, and minus this x star is equal to basically g x star. This is because this is the fixed point. So, having this, what we apply the mean value theorem here, g x k minus g x star. By mean value theorem we can write g prime. So, there is a point between this x k and x star. So, that we have g prime at xi and x k minus x star. So, that is the mean value theorem which we usually write like f b minus f a over this b minus a, and there is a point here xi. So, this fixed point, this mean value theorem we have applied there. So, this xi lies between somewhere in this point x star and x k, and this is the mean value theorem. So, now we know that g prime, the derivative is less than rho in the whole interval a b. So, wherever we are here. So, this g prime is less than equal to rho, and using this there. So, x k, this error is less than rho into x k minus x star, and again we can do this by induction, that it is a rho 2 and then here k minus 1 will come, and then rho 3 and so on. So, we have this relation that this error here at k plus 1th step is less than the rho power k plus 1 and the error at the beginning x naught minus x star. Having this, it is clear, since rho is less than 1, that is the condition we should have, that the derivative is less than 1. So, this rho k, this will go to 0 because rho is less than 1, and this error here as k approaches to infinity will go to 0. So, that is the proof here we have. So, what is the condition? That this g prime should be less than 1 in the interval which contains the root and the initial guess. Coming to the geometrical interpretation of this. So, we have y is equal to x, this line, and we have y is equal to g x, the graph of this curve, and looking at where x is equal to g x. So, this is the point here. So, it is the root actually alpha which we call, and this is what we are looking for. So, we start with some initial guess x naught, for instance here, then we compute x 1 by this g x naught, and so this is the point here x naught x 1, x naught x 1, and then so this is exactly x 1 at this point, because here y is equal to x line it crosses. So, this is the height was this x 1, and here both are equal. So, this is also x 1 now here, and this cuts this graph there, which will be x 2 now. So, this is our x 2, or this is x 1 x 2, and further we will go. So, this is your x 2 here. So, what we observe that we started with somewhere here, x 1 was there now, and x 2 is closer to. So, this is the actual root we are looking for, this is our alpha. So, we are going close to this alpha, and then we have further the x 3 will come, and then we have this x 3 here which is further closer to this point, and then we will continue this and will approach finally to this point. So, this is the idea of this fixed point iteration method. So, we will go with the example here x cube minus 5x plus 1, the same example which we have considered earlier, and let us compute that root which was 0.20 and so on. So, we rewrite the equation now. So, there are several ways of rewriting. So, the first approach we will consider other way also for rewriting this one. First, we are taking here that we have taken the 5x is equal to 1 plus x cube, and then x is equal to 1 plus x cube by 5. So, this g we take and then set up the iteration. So, x k plus 1 is equal to this 1 plus x k cube by 5, and note that this g prime which we can compute from there, it is a 3x square plus 5. So, if we know that the root lies between this 0 and 1. So, if we choose this 0.5 as the initial guess in this interval, and we are sure also in this case that whatever values in this interval, this g prime x is less than 1, because the 0 to 1, and then we have here the condition. So, the sufficient condition for the convergence is satisfied. That means, if the sufficient condition is satisfied, for sure this scheme will converge. If it is not satisfied, then we are not sure whether it will converge or it will not converge, because we have here only the sufficient condition, not the necessary and sufficient condition. So, having this, we start with x naught, for instance 0.5. We can choose actually any initial guess between 0 and 1, and this condition makes sure that it will converge, not only for 0.5, but any other guess also. We can take 0.1, we can take 0.8, 0.9, etc. It will converge. So, for instance, if we take 0.5, then we compute x 1 from this iterative scheme, 0.22, then 0.20 and so on, and we see this 0.2016. Here also it was 0.2016. So, after this fifth iteration itself, the scheme seems to be convergent. You have 0.2016 here, also 0.20. So, there is no change happening up to this 4 digit. So, this is a very good approximation if 4 digits are considered, 0.2016. What we will also see in the same scheme, for example, if we take initial guess here 2.5. So, having this initial guess 2.5, that means our interval which contains the root which was 0.20. So, up to this 0.25. So, our interval, let us say from 0 to 2.6 or 2.5. So, this interval contains the root, but the problem is now if we check that g prime for this value, this will be greater than 1. So, now this time the convergence is not guaranteed. If we take this initial guess, it may converge, it may not converge. So, if for example, if we compute x 1 here, x 2, x 3 and x 4 itself is telling that it is going somewhere else, 10 raised to the power 5, a very large number. So, it is not converging in this case, because our initial guess we have taken 0.25, and in if the interval we consider which contains the initial guess as well as the root, that means it is a 0.2 to like 2.6 something. If we consider this interval, there are points here where f g prime is not satisfying that sufficient condition. So, here we were not sure actually whether it will converge or it will not converge, but actual computation shows that it actually does not converge. The iterations are diverging towards plus infinity. So, what we have seen now, just a remark that g prime was 3x square by 2 in both the cases. In the first case, the g prime was less than 1 and hence the convergence was guaranteed, whereas in the second case, the interval containing the root and the initial guess, the g prime was greater than 1 at some points, and hence the convergence is not guaranteed, which is also reflected in this numerical calculation. What we do now, if we rewrite the equation, for example, in this way, that x is equal to minus 1 over x square minus 5. So, there are several ways of rewriting this is one of them. And now, if we take the same initial guess 2.5 and we check now that it is converging to this root. So, by just rewriting the equations, the same initial condition may converge to the determination of the actual root, And here what we note that G prime is this 2 times this absolute value x square minus 5 whole square, and in this case also the interval containing the roots and the initial guess G prime was greater than 1. So, what is the message? Because this is the sufficient condition that G prime absolute value should be less than 1, then we are sure that the iterations will converge. For example, in this case it is greater than 1, it may converge and it may not converge, and the numerical calculation shows that actually it converges in this case, whereas just in the before case 2 what we have seen that G prime was greater than 1 and the sequence does not converge. So, these are the sufficient conditions. So, if we have that condition fulfilled, then we are sure that it will converge. If it is not, then it may converge, like in case 3, it may not converge like in case 2. So, these are the references we have used for preparing this lecture, and just to conclude, we have discussed the bisection method, and this was an iterative approach that narrows down an interval that contains root of a function f x, and most important in that approach the convergence is always guaranteed. The second approach we have discussed the fixed point method, where it was based on rewriting this f x equal to 0 in this form x is equal to g x, and having this we can set up the iterations there, and the convergence of this method was dependent on this g, and if we have this condition that G prime is strictly less than 1, then the convergence is guaranteed. And as a we have seen also several cases that it is actually sufficient condition. If this condition is not fulfilled, in one case the convergence was achieved, in other one it was not achieved. So, that is all for this lecture, and I thank you very much for your attention.